Hi, I'm Justin Sachs. This is my TAU analysis of a chemical manufacturing plant. The chemical plant that I'm doing a TAU analysis of is owned by a multinational chemical manufacturing company. Within the site that this plant is run at, there's multiple other chemical manufacturing lines. The product line that I'm doing the TAU analysis of is manufactured from refining trona. Trona is a natural occurring mineral and is mined underneath the plant at our mine, which is mined at 1,600 feet. The key thing about producing soda ash and soda ash products from trona is it creates significantly less pollution than our competitors using the solvay process, and it's also more cost effective. The plant that I work at, the plant that the TAU analysis is of, it produces specialty soda ash products, which is not a commodity opposed to regular soda ash products, and we are the only manufacturer of these products. Here's an overview of the plant, and we have the plant that manufactures these specialty soda ash products is run 24 hours a day, 365 days a year, so it's a continuous manufacturing process. And this plant is only run with one operator at a time. It's the smallest of all the manufacturing lines that are on site, and the operators work 12-hour shifts. There are 4 different shifts, and there's 10 quality operators that can run the plant. 4 of the operators are designated operators. The other 6 fill in for when guys are on vacation. The plant can produce either grade A sodium sesquicarbonate or grade B sodium carbonate. The key thing about these two products and with this plant is it only can produce one product at a time. So when there's a switch between the two products, there's a significant changeover period that must occur that affects duty cycle. And then every 5 weeks we conduct a planned 16-hour outage to conduct planned maintenance. Here's a little bit more in depth of the two products we have here. We have grade A sodium sesquicarbonate, which is used primarily in healthcare products such as bath salts, and the majority of it is for exports into the Japanese market. And then sodium grade B sodium carbonate is used primarily in animal feed, which allows animals to eat more, releasing gas by belching, and allows them to fatten quicker within feedlots. Here's the two processes. Below you'll see trona, which is sodium sesquicarbonate essentially. We dissolve it, add additives to it, and then recrystallize it, and that's a great simplification of the process. But when we recrystallize it, that's the key thing about this is the size of our crystal that's formed for using in the bath salts and other healthcare products. Then with our grade B sodium carbonate, we dissolve trona. We run that dissolved trona through an absorber with CO2 gas and additives, and out comes sodium bicarbonate. Here's the application of the TAU process. So in the past few months, we've had significant delays of our products to our customers. Because of these delays, we're running a risk of losing some of our current customers and potential customers because of the time to delivery of the products to the other plants. We're considering expending additional capital to increase the capacity of the current plant, but before we do this, we need to determine if our existing plant can meet the needs of our current and future customers. So the scope of my project was and is to conduct a TAU analysis of this chemical manufacturing plant, determine if I can recommend to management improvements in availability, duty cycle, and efficiency to improve production output with existing equipment. For my data collection, I conducted it for between a 5-week period between the planned outages, which include one of the planned 16-hour outages. I picked the last period when I started this project, which started from August 11th, 2014 through September 14th, 2014, so it's a 35-day period. The majority of my data was collected through our Pi system software, which automatically collects on servers the process outputs, and then I just moved it to Excel with a Pi add-in for analysis. I collected my data points on an hourly basis. I try to collect them on a minute basis, moving the software from the Pi System software servers to Excel, but it kept on crashing, so I had to move to an hourly basis for my data collection. And then I took the values. Once I did analysis of my data, I took the TAU values and averaged them for each day in that period, and then I used that for analysis for my regression. Additionally, I used copies of our operators ISO log sheets from the business archives to assist with the analysis. Here's a sample of my raw data. This is what some of the Pi data looks like when it's imported in Excel. I have the day, I have the different pieces of equipment across the top, which help me determine when I'm making the two different grades of product and assign time to availability, downtime, and then the efficiency and yield. On the far to right, you'll see our product specs, which is bulk density in pounds per square foot, and then total alkalinity. And then the other data you see is just, like I said before, to help me determine the different components of the TAU. Here's my equations that I developed for my TAU analysis. Pretty similar to what we've gone over in class. I have my total time minus my planned downtime, my unplanned downtime, idle time, and utilities unscheduled downtime and over total time. That's for availability. My utilities unscheduled downtime, we produce our own steam, electricity, and different sources of treated water. So if there is a unplanned downtime at our utilities department, I'm unable to produce the products. For our duty cycle, I have runtime minus setup time plus changeover time over runtime, and runtime being here like it is before, availability times total time. And then my setup time, I have filling my system, which is filling the manufacturing plant with treated water, and I have saturating the system, which is where I'm adding the sodium bicarbonate or the sodium sesquicarbonate to the system. I'm building excesses when I'm building the amount of carbonate in my system. So these are the items that go into the setup time. My changeover time is when I strip and boil the system. This occurs when I'm changing between the two products. My efficiency, I have my output of one of my pumps, which is my P204 pump, over 185 gallons per minute. The 185 gallons per minute is a historical moment of excellence that we have used in the plant for our efficiency analysis. And then my yield is essentially product inspect over total product. And the difference between a chemical manufacturing plant and from other plants is when you have product out of spec, the whole lot of product is bad, so you can't separate good product from bad product. So either 100% of your product is good that you're manufacturing at the time, or none of it is good. And below the TAU normal equation, where I have availability, duty cycle, efficiency, and yield. Here I have my plant TAU versus output. Here I've combined the two products and done a graphical analysis over the period when I was collecting the data. The key thing you can see here is you'll notice that availability doesn't correlate as well as the other components to output of the plant. Here I've done the same thing, but I've separated only to grade A. And here I've done it with grade B, and you'll see the split in time. That was when I manufactured grade A, and grade B was being made. So grade A, where you don't see any data collection, was being made, and grade B was made on both sides of that product. Here for the plant regression, I did with assistance of John, we did the regression of the plant TAU against output, and you can see by the R-squared value that there was really poor correlation between the TAU value and the output of the plant for determining what we were manufacturing. Here we've done the regression against the TAU components. R-squared value went to 0.996, so there's a high correlation between the TAU components and the output of the plant, and this is where I've combined once again the two products into the data set, and you can see where it might be equation at the bottom to determine output of the plant. Here's our grade A, which is the sodium sesquicarbonate, TAU regression, TAU against output for the regression, R-squared value of 0.584, which has little correlation to the output of the plant. Here it's broke down into the TAU components for the sodium sesquicarbonate, and you'll see that my R-squared value goes to 0.993, and the output of the plant is determined by efficiency and duty cycle being the largest contributors to the production of the plant. Here I have my grade B for the sodium bicarbonate TAU. TAU versus output. I have R squared of 0.807, which is the best of all the TAU regressions for the plant, grade A and grade B. Grade B has the highest correlation, but if we go to TAU by components, the R squared value goes to 0.998. And below you'll see that with efficiency and duty cycle and yield, here yield's brought in, but efficiency and duty cycle being the constant across both the plant and both grades of product for areas where we could improve the output of the plant. Here's my moment of excellence. You'll see large differences in the moment of excellence. The way I interpreted this analysis is that we have a lot of room for improvement for the output of the plant without large investments of capital. So based upon my conclusion of my analysis, the TAU analysis determined that the output of the plant is highly correlated to efficiency and duty cycle for both grade A and grade B products and for the total output of the plant when combining the two products. There was large difference between the moments of excellence, 42.1 for efficiency and 30.67 for grade A for efficiency and duty cycle respectively, and 30.6 and 28.7 for efficiency and duty cycle respectively for grade B. So this, like I said previously, suggests that output can be significantly increased without a large capital investment. These are the recommendations that I made to my management based upon my TAU analysis. The bottleneck for both processes are our centrifuges. So I recommended we tuned our centrifuges to increase the output of plant. This is a relatively low investment of capital to do this, and doesn't require any new pieces of equipment. The other recommendation I made was the changeover periods between the two 5-week outages to start either with and to only have one product change within that 5-week period. Generally, we tend to make 3 times as much sodium bicarbonate as we do sodium sesquicarbonate. So by doing that, if we forecast ourselves well enough, we could only have one changeover period of the products between the 2 5-week outages where we do our planned maintenance. And lastly, it was to sanction a team with both our operators and management, include them in this process, so we could determine how to improve our duty cycle by decreasing the time we need for filling, saturating the system, building the excess, stripping and boiling the system. This could be a relatively low investment of time and capital, and we can significantly increase the output of the plant if we can bring our total duty cycle time down between product changes. That concludes my presentation.